So I wanted to introduce Jasmin Roissy, that's going to give her last talk on this mini course on wonder domains, please.
Thank you very much. So as I did yesterday, I already prepared something from yesterday's lecture. So today what I'm planning to do is to, well, first, we're going to see the proof of this result that I put on the slide yesterday. So this is the result telling to us that in higher dimension, the result of Sullivan, so Sullivan's result telling to us that on the Riemann sphere, you will not have any wandering domain. It is no more true in the compact case in higher dimension. So of course, once you prove it in dimension 2, then you can always put it in any dimension because you can simply add easy dynamic stuff in the other variables. Okay, and what I told to you yesterday was, oh, look, actually, this will be related to a theorem by Laver, which is highly one-dimensional. So we talked about parabolic implosion, and which goes back to the iteration of a polynomial map, a one-dimensional polynomial function of this form, which is, if you see, exactly of this form, except that instead of adding something which is moving also in W, I'm just adding a epsilon square, which is always the same. So epsilon n, I know that it's going to behave like pi over 2n. And what Laver's theorem tells us is that, well, after 2n iterates, we pass through the arbiter, and the iteration of this map will behave like the composition of the repelling for2 parameterization with the attracting for2 coordinate on the basin of F0, where F0 is simply F. I don't know why I put F0 here. It's simply F. Okay, the non-perturbed map. All right. And I also told you, oh, look, and actually if A is less than 1 and near enough to 1, then this map, this function, has an attracting fixed point, which will be in the parabolic basin of F naught. So okay, I will simply leave here F naught and add a naught in here so that I'm happy, I'm consistent with my notation. So let me first explain just very fastly why I said that this one-dimensional result is related to the iteration of my map. So this is because, so let's see what happens when we iterate our map F, capital F. When I iterate my capital F map, well, so I didn't put any names, but I should. So let me add names in here. So this map will simply be G of W. And this will simply be F of Z. And then, well, I have this perturbation, okay? So when I iterate capital F, I'm iterating on the W coordinate, I'm simply iterating my one-dimensional function G. Okay, and this is tangent to the identity, so I put a 42 in here just for, to put a number. I could simply erase it, and nothing would change. So what happens is that I have the Laver theorem, and I have a parabolic basin for G, and I know exactly what's happening. Okay. So in here, I know exactly how to compute these iterates and how to make them converge. So how to have a for2 component. What happens in here? Well, in here, well, let's iterate one step. So I have this F of Z map. Okay, I iterate F of Z, but I'm perturbating it with something dependent on W. So when I iterate a lot, so let's iterate a lot. Okay, let's iterate a lot. So for n big, well, let me put Gm, m. I iterate m times W. This is more or less like 1 over m if my W was in the parabolic basin of G. Actually, I can already take it in the parabolic petal, so in the attracting petal of G. So in here, somehow, what happens when I iterate one time more? So Fm plus 1 of ZW, well, I'm going to have F of, say, Zm plus pi squared over 4, 1 over m, more or less. And in here, I'm going to have 1 over m. So so somehow I have a perturbation of my map with something small, which is of this form. But what happens when I iterate once more? Well, when I iterate once more, in here, it's going to change. So what's happening is that I am composing. So when we iterate more and more, we compose. We have the composition of one-dimensional transformation. So transformation of the form F plus epsilon k, where actually, so in here, I don't like it anymore because I made my life a little easier. So I put a square in here and I put a 4 in here. So what I want is to have m squared, for example. So let me iterate m squared times. So I have a square in here. And so I will be in the same situation that I had for Laver's result. I'm able to put an epsilon m squared. Okay, so epsilon k squared, for k at least, well, let's say we go, so how do we get from m squared to m plus 1 squared? Well, I have to iterate 2n plus 1 times. So to get to n squared to n plus 1 squared, well, this is simply n squared plus 2n plus 1. So let's see what happens to get into two fibers of the form n squared. And in here, epsilon k squared will be more or less of the form pi squared over 4 times m squared plus k. So you see in here that I am doing something which is similar to what we did with in Laver's result. So even if I didn't prove it, but you had an idea, right? You have, I think, let me go back to my previous lecture. Yes, I did this, this picture over here. And remember, so this perturbation leaves this corridor open, and the time to pass from this attracting green region to this repelling yellow region was 2n. In here we had 2n, but we were iterating always the same map. So now what we are doing is that, well, we pass from an autonomous iteration to a non-autonomous one. At each step, I'm changing W in here. So I'm adding this kind of, well, epsilon squared, but at each step, I'm adding pi squared over, not adding, I'm composing f plus epsilon k squared, where epsilon is pi over 2 n squared by, pi squared over 4 n squared plus k. And so, well, the magic of this is that, you see, I told you, oh, to get from n squared to n plus 1 squared, it's an easy computation. I need 2n plus 1 steps. And what we were able to prove, what our key proposition is the following. So key proposition, we need exactly 2n plus 1 steps to pass through the F-beta this time in this non-autonomous situation. So let me write it down. in a correct way. So as n goes to infinity, the sequence of maps sending z times w to, I take the 2n plus 1 iterate of the point z gn squared w converges locally uniformly on, well, the basin of f times the parabolic basin of g to the map, well, z times w goes to, well, in the sum coordinate, I know exactly what's going to happen, because if I take any point in the attracting basin for the origin for g, then this sequence has to converge to 0. Okay, so I got a 0. And in here, what I'm telling to you is that we get back our one-dimensional Laver's map. So we started from a point in Vf times Vg, and we land to a point which belongs to C cross 0. And remember that I told you that if I'm able to choose my initial A, I'm sorry, I have to go back like this, which is a little annoying, I think. So I'm able to play with this parameter A so that my Laver's map in here as an attracting fixed point. And this attracting fixed point is all I need to prove now that I have a wandering domain. So I think, yeah. So let's do it upside down. So let's leave this key proposition for the moment at a side. So we know it, we have it. And we also know that we can choose, well, essentially we can choose F, so we can choose F so that its Laver's map as an attracting fixed point psi in the basin of F. And why is this so important? So this condition is very important for me because, well, remember what happens in the parabolic basin. So in the parabolic basin, in the cauliflower, that I'm not able to draw, but again, so here I have the origin. What happens to a point in here? Well, a point in here will converge on the iteration by F to the origin. So in particular, it is never going to be pre-periodic. Okay, it will always try to go, well, it's every image is different from any of the previous one. So let me put it here as a remark. For every z in B of F, well, say, let's change the name because everything is called z. For every zeta in the parabolic basin, fk of zeta is different from fj of zeta for all k different from j, which means that zeta is not pre-periodic. Okay, and this is the other important thing that we're going to use to construct our wandering domain. So now let's see the proof of the result by using the key proposition here. So this key proposition and the fact that we have an attracting fixed point for this one-dimensional map in the parabolic basin of little f. Okay. So let's see what this means. Okay. So, well, this is exactly the proof of well, the theorem on wandering domains. Once you have these two facts. Okay, so zeta, so psi is an attracting fixed point for the Laver's map. And so there exists, well, V, a small disk, in the parabolic basin of F, which is contracted by the Laver's map. So that when I consider the image under the Laver's map, it is compactly contained in V. And moreover, I know that if you consider the entries of this Laver's map restricted to V, they will converge to psi as k tends to infinity. Okay, so I have in my cauliflower here, I have a small disk somewhere around psi where I know that it is going to be sent into itself, okay, by the Laver's map. Let me enlarge it for a moment. So this is the Laver's map. Okay, so this is the first thing that I want to take. And let's see what I also have. In here, I also have G. So I have G, and I know that Gn is going to convert to 0 whenever I pick a point in the parabolic basin of G. And actually more than this, it's going to converge uniformly on the basin of G. And so, well, let's take the easiest thing that we can take. So let's take W, be again a small disk, but this time compactly contained in the parabolic basin of G. So now what I would like to do is to take V times W. So this is what you would like to take, but we can't. I mean, this is not what we are going to take. So because what we know is that now we want to use this key proposition, and this key proposition is telling to me that I will have to consider this sequence of maps. Okay, so now I have to be more precise. So what the key proposition tells me is the following. So the key proposition tells us that, well, there exists n0 bigger than 0, so that starting at n0, what we are going to have is that the proposition on the projection on Z of the 2n plus 1 iterate of V times G iterate n0 times of W, this is going to be compactly contained in V, where pi of Z is what you expect, so the projection on Z, so Z times W sending to Z. Okay, and now I say, okay, fine, so I will take this guy. Well, it's not exactly the right thing to do because, well, I know nothing on this guy, and actually I want to iterate something. So let me tell you what I'm taking. So I take U, a connected component of n minus n0 of this guy. Squared, sorry. Yes, V times G iterated n0 times of W. Okay, so I take something. I take this set. Well, actually, I can't take this set because I don't know whether or not it is connected. I'm taking three images of a set. So, okay, I'll take a connected component. And what I claim is, so lemma, F iterated n squared times converges locally uniformly on U to psi 0. So why is that so? Well, this is an easy exercise, and it comes from the fact that, well, there is one part which is exactly completely stupid, which is coming from the fact that I'm iterating a one-dimensional map on its basin of on its parabolic basin at the origin. So, well, we already proved, Lo and Fatou proved that it was going to 0. So we can't have something else. And the fact that now we are going to converge to the fixed point of the Laver's map, it is because, well, what we did, we had this key proposition telling to us that we are approaching these maps with the Laver's map. And now, well, we took a point which is attracting for the Laver's map. And so, while we are working in this small disk, the Laver's map was converging to this fixed point. So our sequence of map has to converge to these points as well. So this is an easy computation. This is not difficult to do. But now let me see what this means. So this means that U is contained in the Fatou set of capital F. Because whenever I take a sequence in the family of iterates of capital F, I can take the subsequence given by the squares. And I know that on U, the squares, so the square iterate, I don't know how to say it better, so Fn squared converges somewhere, locally uniformly. So U is inside the Fatou set. But U was a tiny little open set somewhere in C2, okay? So, well, it is contained in the Fatou set. Therefore, there exists omega, a Fatou component, such that U is contained in omega. All right. And what happens to Fn squared on this Fatou component? Well, on the Fatou component, by analytic continuation, we have that Fn squared has to converge to psi 0. Because if it is converging to psi 0 on a non-empty open set, then it has to, which is contained in omega, by analytic continuation, it has to converge to the same fixed point. Okay, for the Laver's map, to this point. And then I'm almost done. So I found a Fatou component where I know exactly what's going to happen for this sequence of iterates. And now the only thing that I'm left with doing is that to prove that omega is our wandering Fatou component. And to prove that, well, let's see what happens to, well, we want to prove that, well, if I take fk of omega is different from fj of omega, fj is different from k. Okay, let's see. Well, and to do that, I'm going to use simply uniqueness of limits. Well, Fn squared plus k converges to what? To f iterated k times of psi 0 on omega. So what I'm doing in here, I'm simply taking this convergence and I'm composing by f, capital F, k times in here and k times in here. Okay, so this is not difficult. And in here, I know exactly what this map is. This is little f of psi 0. But this means that if I now read it in a different way, what I'm saying is that Fn squared restricted to fk of omega is converging locally uniformly to little f of psi 0. All right, so, and Fn squared, let me write the obvious, on the jth iterate of omega under f is going to converge to the jth iterate of psi 0. And now, so to have fk of omega, sorry, this omega is not readable. equal to fj of omega for j different from k, we need to have fk of psi equal to fj of psi with j different from k, which is not possible because we are in the parabolic basin of f, which is not possible because psi belongs to the parabolic basin of f, and so it is not pre-periodic. So, well, let me review this with a picture. So what I'm saying, I'm not very good. I had a very nice picture in one of my talks that I stole to one of my co-authors. I think it was Mathieu Astorg, who is very good in doing pictures. I'm not in doing pictures, let's face it. But well, let me at least try. So I have my invariant fiber here, W equal to 0, and I have somewhere psi, the point psi 0. And what I'm saying is that, well, gray is not a good. So what I'm saying is that I have my little u in here that for me is just a square. And I iterate some. But then when I iterate at so this is n squared, this is n plus 1 squared, and I have 2n plus 1 iterates in between. So what's happening is that this tiny u is going to converge to this point, okay? And what I'm saying is that, okay, if you now, I should have done a little more iteration, and it's taken longer and longer, okay? To get back here, so now if I take one image, say the first image because it's easier, well, this is going to converge to f of psi 0. And since I know that these two guys are different and always different, then the component cannot get back to one of its images. So this was, so you see, now you know exactly the proof of this result. The only thing that for the moment you don't know yet, and well, actually you will only know the heuristics on how we proved it, is this, let me go back, yes, is the proof of this proposition here. Okay, so, but once you have these two propositions, well, the proof is more or less easy to understand, I hope, at least. So let me finish with giving to you the ideas. If you have a question, you can go.
Jasmin,
yes.
Can I ask you, please, if I understood the structure of the theorem? You cook up a skew product, which is on one side a parabolic map with perturb, and on the other side a parabolic map,
yes,
such that it converges under some iterate to, on one side, the Laver's map of the original parabolic map F, and on the other side,
0,
a fixed point 0.
Yes.
And then you know that since the Laver, and then there is the Laver map that has to change at every point. I didn't get that step.
No. Actually, what I'm using is the fact that the Laver's map has a fixed point inside the parabolic basin.
Mm-hmm.
And now I simply use the fact that when I'm here, when I consider I take fn squared and I iterate also more, k times more of f, well, the image of psi 0 under capital F is simply the image of psi under little f and 0. Okay, and once I'm here, now I just use the fact that psi is a point in the parabolic basing. So this is
and every point is going to be different because you are in an attracting basing, and then you keep moving like that, and this
Exactly.
is why you have a wandering domain. Okay, thank you.
Exactly. So what I didn't explain to you yet is, okay, I could also simply tell to you, so let me try and do this, and then we'll see how far we can get. So the first thing that I can tell to you, so okay, very zero thing, is the fact that you have an attracting fixed point for the Laver's map. This is a computation. I mean, this is simply a computation. And before I forget, let me also say that there is a newer version of this result. So say you don't have an attracting fixed point for the Laver's map, but you have an elliptic fixed point, which is a fixed point which has multiplier and irrational rotation. Then you might hope to accumulate on a circle. And the answer for the moment is no, but you still have a wandering domain. And this is a very recent result by Astorg, Bachtaler, and Peters. But the construction is more or less the same. Okay, the only thing that is that now you don't have an attracting fixed point anymore, so you have to change a little the end of the proof. But they still have these, well, they start with a key proposition in here. So this part comes from dimension 1. You don't need to be wanting to search for a wandering photo component in higher dimension to prove this result. It's just a computation. And in here, what is this proposition doing? So let me, yes. So the idea of how to prove the key proposition is what I think, did I write it down here? Sorry, I already forgot what I said. That's terrible. Yes, I did it in here. So yeah, okay, fine. So in here, what's happening is that what one has to do to prove this key proposition, which is down, is to look at the proof of Laver's and say, oh, look, what is going to happen? And what is happening is exactly what I told you at the very beginning today, meaning that I'm composing a non-autonomous sequence of maps, each depending on the other, and I have a decay in the epsilon case, because epsilon k squared is going like pi squared over 4 n squared plus 1. Okay, and so at some point you have to say, okay, this time instead of taking 2n steps to pass through the arbiter, I'm taking exactly 2n plus 1 steps. Okay, so this is a computation, so the number of steps is somehow magic, but the idea on how to prove that we have this sequence of map is converging to the Laver's map and 0 on the other side comes from the proof, from the original proof of the theorem of Laver's. So I would like to spend the last 10 minutes of today in telling to you at least what one has to do to prove such a result. Okay. And I think I didn't do it yesterday. Yesterday I was doing only my pictures, but I didn't tell to you anything about something more precise. Okay, so just an idea of how Laver's works. So idea for Laver's theorem. So remember that what did we have? So we had I epsilon, we have minus I epsilon, and I had this 2 region in here. And so what I told you, and when I tell you again, is that whenever I'm far away from a neighborhood of the origin, iterate in f. So in here I have f of z, which is z plus z squared, and f, what did I put? I think is f epsilon squared, but I'm simply taking, yes, f epsilon squared of z is simply, yes, just epsilon n squared. And my epsilon n is simply going to be, well, like pi over 2n. Okay, so whenever I'm far away, far from the origin, the error that we do by iterating f instead of considering the iterate of f epsilon n is not much. It's just we don't care. So we can approach, so the orbits of f and f epsilon n are, well, nearby. So what I'm saying is that if this is the orbit of f and this is the orbit of f epsilon n, so I'm just following, so the two follow. So, well, the error that I'm doing is very minimal. But now I entered in this neighborhood of the origin. And now, yes, and now what's happening is that now I know exactly where my two initial points are, but now I'm at the size where iterating this map or iterating this map makes a difference, because epsilon n, my contribution, is going to give a contribution. It's going to move a little more. Well, in principle, it could move a little further from what f would have done. And of course, when I'm in this region, it's even worse, because f cannot cross, orbits under f cannot cross this 0 point, whereas the orbits under f epsilon squared, they can. Okay, and so I can, yes, I can divide my neighborhood into 3 regions. So there is one region, which is the ingoing region. There is this passing through the beta region. And the third region is the outgoing region. So what I have to estimate is the following. So I enter in here and I know exactly where the orbit, the iterate under f and the iterate under f epsilon squared are. Then I get here to this region where I'm passing through the agbeater, and so I will forget about the orbit under f because I can't control it anymore. And I will see how many steps it takes to go from here to here. And in Laver's result, we get 2n steps, and this is just a computation. And then now I get here, I just exited from these 2 region, second region. And now I want to compare again what happens to the orbit under f epsilon squared and what happens to the orbit under f in this outgoing region to know where I landed when I'm here. And once I'm outside of my region, then iterating f epsilon or iterating f, it's exactly the same. Okay. And so, okay, let me choose a less colorful color. And so what happens in this ingoing region? Well, remember what we did in the Lofa-2 flower theorem. We didn't exactly work in the petal. What we did, we went to infinity. So we sent the origin to infinity because in there, our dynamics was more or less the translation by 1. And I also told you, well, look, we have the attracting Fatou coordinate, which conjugates, semi-conjugates the dynamics exactly to the translation by 1. And so the idea is that we have the Fatou coordinate of f, and we want to use somehow an approximated Fatou coordinate in this region so that we are able to see something about the iterate under f and the iterate under f epsilon squared. And I think, yeah, I have 5 minutes, so I will just tell you this and call the day for today. So when you enter, so say that ZIN is, let me write a little bigger. I don't know why I'm writing so small. Is the point where I entered in this region. So in here, when ZN is small but not too small, we have that phi f0. Oh, it's little f in here. Sorry, it's f not in my notes of zi kn is going to be like phi f of f kn of 0 plus a little o of 1 as n goes to infinity for kn, which is of the order n to the power alpha, well, the integral part, of course, of this, where alpha is a number in between 1/2 and 3/2. And so zk and I is more or less like -1 over kn, which means that phi f of zi kn is more or less like phi f of f iterated kn times at z. Yes. Which is now I'm using the fact that this is my attracting photo coordinate. So this should be phi f of z plus kn. Okay, and to do this, so the tool in here to prove this is approximated for two coordinates. So we know exactly what happens, so which kind of point I have when I enter these two regions. Well, I pass through, so we take 2n plus 1 steps. So a computation gives 2n plus 1 steps, so iterates to pass. Sorry, I don't know why it's 2n plus 1 now. It's 2n because I'm doing Lavers through the arbiter. And now in the outgoing part, yes, I have 2 minutes, so I will close it there. In the outgoing part, we do the same. But with, well, in here, when I'm going out, if I was just studying F, I would have been in the repelling data. And so I can use the repelling for two parametrization. So the repelling. For two parametrization. And so at the end of the day, we prove we have that. So at the end, we get Z2n, which is simply f epsilon n squared iterated 2n times of z, is behaving like the repelling for two parametrization composed with the attracting for two coordinate at z, which is simply the Laver's map at z. And a good exercise, and I will finish on that. So if you didn't like this proof at all, just to convince yourself that this should be true, you can simply check it. So this is not a polynomial, but this is so nicer. If you take f of z, which is z over 1 minus z, then the repelling for two parametrization of u is simply minus 1 over u, and the attracting for two coordinate is simply minus 1 over z. And so the, sorry, I don't know why this is a plus. This is an equal. So the Laver's map is the identity. and you can do the computation by using pi over n squared, and you can compute exactly and prove the convergence. So this is a nice way to convince ourselves that this should be correct. I don't know how Laver did it, but I guess maybe he started with an example. So this is the easiest example possible because everything is explicit, even if it's not a polynomial. And then you can go back and read what one do. So one of the, from my point of view in this theory, the most annoying part is to understand why the approximated Fatou coordinate are what they are. So it's a formula. You have a formula and you have actually a sequence of maps. And one can say, oh, they converge to the attracting Fatou coordinate on this side and the repelling Fatou coordinate parameterization on this side. So this is a little too much for me. This was a little too much when I entered in this kind of stuff, but it was easier to understand it on this exercise here. And what we had to do was to change, well, one of the most difficult part was to change the approximated Fatou coordinate, because in our case, well, the epsilon k's are varying at each step. So the 2 points in here, these 2 points are also moving in the space. So yes, I think I stole you 1 minute, so I will stop it here, and thank you very much for your attention during all the lectures.
Very much. Are there any questions or comments? Let's see, Luna?
Jasmin, I lost. What is the fact that guarantees that your Laver maps you converge to has an attracting fixed point?
So actually, what we use is let me check it. It was somehow some perturbation theory. So if you have that A in here, so where is it? Let me go back. So let me go back to this statement where everything is there. So in here, when A is 1, you can prove that you have a parabolic fixed point for the Laver's map. But having a parabolic fixed point was a bit too much. I mean, we had already 3 parabolic fixed points. It was not enough to prove convergence. I mean, maybe it is, but the computation were annoying enough. And so the idea is that whenever you have this A here, well, you know exactly how, so I didn't put it here, but I think I put it there. So in here, this B is 1 minus A. This coefficient in here is 1 minus A. And so you can compute the first coefficients, well, the first derivative at the end of the Laver's map at this fixed point by moving A. So the computing it is not so easy. So I think at the end, the proof that is in the paper is a more elegant proof, saying, oh, look, if you have a parabolic point by perturbation, you will get to an attraction fixed point if A is small enough and close to 1.
So basically, yeah, you are saying that the A is the one that gives you the multiplier of your Laver map, because it's the one that appears. Okay, this is why this works for whatever A less than 1 and sufficiently close to 1. Okay, very, very, very nice. Very nice. Thank you.
Thank you.
Are there any other questions, comments? So I have a question about this. As far as I remember, I think there are some results about parabolic petals in higher dimension.
Yes.
I remember a paper of Monique Hakim, I think.
Yes.
Many years ago. It's a very nice paper. So I wonder if there is a Laver's theorem for higher dimensions, and you could apply this to generalize.
Yeah, exactly. So what the problem is, actually, we are working on it.
Oh,
So,
okay.
but the problem is in higher dimension. Say we stay in dimension 2, which is already enough for our life. So when you are in dimension 2, the problem is that, so what happens in the Laver's theorem is that you're having these two petals who are intersecting. So when you open it, you have an intersection. So you can exactly compute the Fatou coordinate and the repelling Fatou parameterization, and they have a place where they both exist. Okay. When you are in higher dimension, then it depends on the petal you search for. You can have a one-dimensional petal and a two-dimensional petal. Okay. And it is no more true that you have a full neighborhood of the origin, which is in general. Of course, you can find example where this is true, but these maybe are very not generic. Actually, they're surely not generic. So what happens is that you don't have a full neighborhood of the origin, which is described by attracting and repelling petals. You have what Akim calls the characteristic directions. Actually, this is a terminology coming from Ekal's work. But anyways, so it's their results. So you have this characteristic direction. So say let me go here. And because I'm moving my hands, but I'm not sure that it is very seeable. So you have, say you have three characteristic directions. And in here, along this direction, these are complex lines. So what you are able to find is that whenever you have this direction are not degenerate in a easy way to define, then inside each of them, you have a flower.
I see.
Okay. But to have something which is exactly the same as Laver's does, well, you would need to have big stuff, so big petals, two-dimensional petals, to intersect them, and that's.
I remember this result of Monique Hakim. I think it's the simplest situation possible to have one eigenvalue with 1, and the others are contractions, right? You have contractions, and in this case, you have like a solid petal.
Yeah,
right?
in that case, actually, sorry, I was thinking about the full parabolic case. Yes, in that case, you have a very nice paper about parabolic implosion for, say, semi-parabolic, semi-attracting case. So this mixed case. And this is due to Bedford, Smiley, and Weda. And you have somehow a similar to Laver's result. So I was thinking about the full, the exact analog, so completely parabolic.
I see.
If you have
so
a complete,
cannot use this to generalize your result, or no? You
No.
cannot use this solid situation. I see.
Not exactly.
I see. Great. Any other questions?
Actually, I have a
Yes.
question that's more perhaps directed to the students, and it's also related to Danielle's question. So, as an expert in the field, what would you say to the students that are the nice problems in which they could work on?
Okay, so that's a difficult question. I didn't prepare myself. Well, actually, so there are a lot of questions, open questions on the classification of already invariant for two components in higher dimension. So already in dimension 2, if you take polynomial automorphisms of C2, which are conservative, then still we don't have the full classification yet of invariant for two components. And of course, you can go to higher dimension and, as well, a lot needs still to be done. So one difficult question was, I didn't mention it, sorry about that. One difficult question was to find a polynomial automorphism of C2 with a wandering for two component. This has been solved by Pierre Berger and Sébastien Bibler, maybe last year or at the beginning of this year. But their technique is completely different from the techniques that we saw today. They are coming, I've been told, from real dynamics. This is it's an 80 pages paper that I'm not yet able to fully understand. That's my fault. But one question, which is pretty natural, is, well, can we find with similar techniques to ours, for example, a polynomial automorphism of C3 with a wandering for two component coming from this kind of situation? So what it is true is that you can do it in dimension 4. So this has been done by David Hahn and Ann Peters. So they have a polynomial automorphism of C4, which is somehow degenerating to our example. And they can use exactly what, most of the result that we had to prove that there is a wandering domain. So this is exactly related to what I said here today, well, in this week. And these are like questions on global dynamics. But there is a relation in with global dynamics and local dynamics. And there are a lot of questions in local dynamics that still need to be addressed. So like a question about normalization, question about, characterizing the dynamics in a full small neighborhood of a fixed point. What happens? So there are a lot of questions like this and many more.
Thank you.
Thank you very much. So I think it's time to thank Jasmin again for the wonderful series of lectures. It was really interesting. So thank you very much.
Thanks to you. It was a very nice audience and a pleasure to be here. Next time I will come to Brazil.
Yes, that's much better. Yeah.